In August 2024, the newly launched XRISM Observatory turned towards a tiny point of light in the Lepus constellation, and its advanced X-ray instruments detected something truly extraordinary. There, at the center of two colliding galaxies, a monstrous black hole had awoken from an eons-long slumber and started firing cosmic bullets into space at blistering speeds. These highly energetic outflows had long been thought to play a pivotal role in the evolution of galaxies, but never before have they been observed in such detail in a galaxy system undergoing intense star formation. This groundbreaking observation is giving scientists a critical insight into one of the most turbulent relationships that exist in all cosmology, that of a galaxy and the supermassive black hole that lies at its heart. The question is, what can it teach us about our own galactic home? I'm Alex McColgan, and you're watching Astrum. Join me today on an odyssey of creation and destruction as we witness epic intergalactic collisions and the jets their black holes produce, events that are thought to play a pivotal role in the lives and deaths of galaxies. We'll take a closer look at the X-ray technology scientists are using to probe the sleep-wake cycles of supermassive black holes and discover just how much their fates are intertwined with that of the galaxies they call home. In our universe, almost all large galaxies are believed to share one mind and light-bending feature, a supermassive black hole at their core. These are colossal objects with masses hundreds of thousands or even billions of times that of our Sun. Take for example Sagittarius A star, the supermassive black hole that lies at the heart of our own Milky Way. The latest observations suggest this black hole is more than 4 million solar masses, contained within a radius smaller than the orbit of Mercury around our Sun. The largest galaxies are thought to be home to true leviathans, with the black hole at the center of the cosmic horseshoe system estimated to be a staggering 36 billion solar masses. Yet, surprisingly, most of these black holes aren't out there hoovering up vast quantities of matter. Instead, they lie dormant, only revealing their presence through the gravitational effects they exert on the stars that orbit them, or the light that passes nearby. Indeed, it's thought around 8 billion years have passed since Sagittarius A star went through its most active period of feeding or matter accretion. So why do supermassive black holes go through periods of intense activity before returning to dormancy? And what effect do they have on the life cycles of their host galaxies when they are at their most awake? Our cosmos offers up one important clue. Thanks to telescopes like Hubble, astronomers have now identified thousands of galaxy systems scattered across the sky with chaotic and tortured forms. We don't think these are actually single galaxies at all, but violent, slow-motion galaxy collisions that over hundreds of millions of years transform smaller galaxies into larger ones. This process is called galaxy merging, and it is now thought to be one of the dominant ways in which larger galaxies come into being, particularly elliptical galaxies. Unlike rotating spirals like our own Milky Way, elliptical galaxies appear smooth and featureless. Their stars orbit in random directions, and they show very little star formation. And astronomers believe this may be related to how they co-evolve with the supermassive black holes that lie at their hearts. The theory goes as follows. As two smaller spiral galaxies approach, they are distorted and stretched by powerful tidal forces. Stars are ejected from their previous orbits, and vast clouds of dust and gas begin collapsing under gravity. This ignites a phase of furious star formation, where new stars can pop into being at a rate up to 100 times higher than that found in other galaxies. Astronomers refer to this phase as starburst. But not all of the disturbed gas and dust in a galaxy merger system is destined to become new stars. Instead, powerful gravitational forces begin drawing much of it directly to the galactic core, awakening the dormant monster at the center, the supermassive black hole. Space is full of some really impressive sights. Just this month we had an otherworldly solar eclipse, and in the next 24 hours you may get to see a lunar eclipse, where the Earth's shadow will turn parts of the moon, but not all, an arresting bloody red. Events like these don't wait for you, and if you want more than a phone photo or a fleeting glimpse, having something you can quickly set up makes a huge difference. That's where today's sponsor, Dwarf Lab, comes in. The Dwarf Mini is a great, convenient telescope for capturing celestial events and vistas. At just 840 grams, I can take it almost anywhere, choose my target in the app, and let the Mini center and track it for me. In fact, this is the solar eclipse time-lapse I captured with the Mini myself. The Dwarf Mini stacks and enhances your images right in the app, giving you results you can immediately show off. So if you're looking for an effective, easy-to-use telescope that you can fit in your pocket, why not scan my QR code or follow the link in the description below? Astrum users will get 5% off if they use the code Astrum5 at checkout. The Dwarf Mini might capture images, but we're talking about capturing matter. And for that, supermassive black holes are king. As matter spirals inwards, it forms an accretion disk that forces particles closer and closer together until they collide, converting kinetic energy into heat, meaning that as matter approaches the event horizon, it forms a plasma, in which temperatures climb towards 12 million degrees Celsius. This process converts the center of the galaxy into what's known as an active galactic nucleus, a structure that generates so much light from frictional forces that it outshines all the stars in the galaxy combined. As the black hole at its center gorges on inward flowing matter, the high speed of charged particles in the accretion disk leads to the formation of potent magnetic fields. At the same time, high-energy photons emitted from the superhot plasma exert a powerful outwards pressure called radiation pressure. Together, these effects are thought to eject some of the material away from the accretion disk as winds, the most powerful of which are known as ultra-fast outflows. Streams of particles whose speeds have been measured as being as high as 90,000 kilometers per second, a staggering 30% the speed of light. And it's these ultra-fast outflows, nicknamed cosmic bullets, that scientists believe could play a pivotal role in the life of an emerging elliptical galaxy. The idea is that as these cosmic bullets stream into space, the high-energy particles interact with cold, dense clouds of gas that are feedstock for star formation, and disperse them, a process that ultimately kills the galaxy's ability to generate new stars. This quenches the starburst phase, and the galactic nucleus metamorphoses into a quasar, a system where black hole activity is so powerful it outshines its host galaxy by up to 1,000 times, and of course suppresses any further star formation. The quasar phase can last for tens or even hundreds of millions of years, until the black hole finally exhausts its food supply of gas and dust. Only then will the supermassive black hole return to dormancy, allowing the new galaxy to settle into its final, mature elliptical phase. It's a neat theory, however, it's one for which the critical stage, where both star formation is still underway and the black hole is waking up, had never been fully observed, until the X-ray imaging and spectroscopy mission entered the stage, that is. Led by Japan's JAXA, the X-ray imaging and spectroscopy mission, or XRISM for short, launched in September 2023. It carried 2 new generation instruments into orbit, a wide-angle X-ray camera and a spectrometer called Resolve that is capable of picking up the most detailed X-ray spectra ever collected. Because X-rays are generated at extremely high temperatures, together these instruments allow XRISM an unprecedented view into some of the most violent and energetic objects in our cosmos, such as supermassive black holes in active galactic nuclei. For the first 6 months of operations, XRISM was in its performance verification phase, the aim of which was to provide the scientific community with data to confirm the telescope could achieve its mission goals, and to showcase its transformational science abilities. And it was during this phase, in August 2024, that XRISM observed an active galactic nucleus in a galaxy merger 603 million light-years from Earth. Now, this may not look like the snappiest of names, but within it lies a clue as to what makes this particular system so attractive to researchers. IRIS stands for NASA's Infrared Astronomical Satellite, which launched in 1983 and was the first orbiting telescope to perform an infrared survey of the sky. IRIS 05189252 was one of a new type of galaxy discovered by the satellite. Galaxies that were enveloped in such thick clouds of dust and gas that any UV and visible light they produced was absorbed and re-emitted in the infrared. They may be invisible to the naked eye, but these galaxies, named ultra-luminous infrared galaxies, radiate more than 100 times the energy emitted by the Milky Way. And the reason they glow so intensely is that those thick clouds of dust and gas were found to be sites of intense star formation. IRIS 05189252 is a galaxy merger in the throes of starburst. The XRISM team, including Associate Professor Noda Hirofumi and Assistant Professor Yamada Satoshi of Tohoku University, knew that as well as being surveyed in infrared, it had also been previously studied in the X-ray band. Within that data were tantalizing clues that this supermassive black hole may have begun to activate. These suggested that this galaxy merger could be at a critical point in its evolution in which it transforms from a starburst galaxy into a quasar. This is a transitional change, thought to only last tens of millions of years, a blink of an eye on cosmic timescales, making it a rare and extremely valuable natural laboratory for studying the feedback mechanisms between a black hole and its home galaxy. And it had never before been observed by an X-ray observatory with the pure resolving power of XRISM. Like other X-ray observatories, XRISM can study the ultra-fast outflows from active galactic nuclei by looking at the spectra produced from what are referred to as helium and hydrogen-like ion atoms found within the outflow winds. You may be forgiven for thinking, how can iron be like hydrogen or helium? Well, these are iron atoms that are stripped of all but 2 of their electrons, so each resulting iron ion has an incredible 24 or 25 positive charge. When X-rays emanating from the vicinity of the black hole are absorbed and re-emitted by one of those iron ions, a characteristic signal emerges at 6.7 kilo electron volts and 7 kilo electron volts respectively. Using these, scientists can work out just how fast the iron ions within the ultra-fast outflows are traveling by looking at how much the signals undergo something called blue shift. Of course, you've almost certainly heard of redshift, the process by which light is stretched towards the red end of the electromagnetic spectrum when it is emitted by stars and galaxies as they move away from Earth, the famous evidence that proved our universe is indeed expanding. However, in our little corner of the universe, where the force of gravity can overcome the local expansion of the universe, there are a few bodies whose motion produces the opposite effect. Light waves are squeezed to the blue end of the spectrum. The most famous example of this is the Andromeda Galaxy, whose slightly blue shifted light indicates it is actually moving towards the Milky Way at around 110 kilometers per second. But a more distant galaxy, like IRAS 05189252, can also lead to blue shifted light when it is ejecting material at high speed in our direction, material like those ultra-fast outflows fired by supermassive black holes. It's by looking at the degree to which the helium and hydrogen-like ion spectra are blue shifted that allows researchers to calculate the speed at which the outflows are traveling. This is exactly the approach that members of the XRISM team were using to interpret the spectra from this galaxy when they found something astonishing. Where previous X-ray studies of the system had found one blue shifted peak at around 7.5 kiloelectron volts, XRISM's more powerful resolving power found 3 peaks corresponding to 3 discrete speeds. This means that the supermassive black hole at the center of the galaxy was spitting out multiple bullet-like outflows of material that were traveling at 7.5%, 10%, and 14% of the speed of light. The team were also able to calculate the energy carried by these winds and found it was more than 100 times faster than the slower molecular winds spreading through the galaxy, certainly sufficient to suppress the explosive star formation that had been observed in the infrared observations. The team also used XRISM's X-ray camera to image the rest of the galaxy merger and revealed that the central supermassive black hole was already absorbing vast amounts of matter. In fact, close to the limit of what is possible for a black hole to consume. That's known as the Eddington limit, and I've got another video about that you can watch here. They are confident that it's this violent accretion of matter that is generating the bullet-like outflows observed by the spectrometer, and at the heart of the galaxy, the XRISM team have explained, is a black hole coming out of an eons-long hibernation, and it's announcing its presence to the host galaxy with a roar. Put together, these findings are some of the strongest evidence to date that it is indeed the gargantuan consumption of material by supermassive black holes that kills rapid star formation in merging galaxies, ultimately leading to the emergence of giant elliptical galaxies with their low rates of star formation. Of course, there is still much to learn. The XRISM team are keen to revisit the galaxy to see if the bullet-like activity of the supermassive black hole varies at all over time, and to work out if any further ultra-fast outflows can be identified. And looking to the future, in the late 2030s, the ESA-led NewAthena mission will launch. This large-scale, international X-ray observatory will be equipped with an even more advanced spectrometer than XRISM. This will allow scientists to investigate each of the evolutionary stages of galactic growth, from the initial collisions to the peak of quasar activity in more detail. But for now, this work provides an unprecedented window into the forces that govern the lives and deaths of galaxies, including our own. Remember the Andromeda galaxy that is hurtling towards us at 110 kilometers per second? It has long been thought that in about 5 billion years, it will collide with the Milky Way, initiating a galaxy merger on our own doorstep. And even though the latest calculations have downplayed the chance of this event coming to pass to around 50%, if it does, both the Milky Way and Andromeda galaxies will cease to exist in a fury of starburst, and a new, more massive elliptical galaxy will take their place. And then, as the colossal clouds of dust and gas are stirred up by tidal forces, Sagittarius A star, the supermassive black hole at the heart of the former Milky Way, will awake from its billion-year slumber and begin feasting again, firing out its own cosmic bullets that will ultimately dictate the star-forming power of its new galactic home, a place that will contain the broken remnants of our own cosmic haven. The Astrum newsletter is one of the most beautiful reads you'll ever get. Even if you're not in it for the news, our photo of the week always makes it worth opening. Sign up with the link below. It's a quick, inspiring way to stay connected to everything happening in the cosmos, from discoveries to missions and the stories behind them. Each issue is carefully designed and written to make science feel exciting and easy to follow. If you already enjoy our videos, you'll love having this in your inbox every week. Join thousands of readers exploring space with Astrum.